Okay, this is my video number 9 for differential equation. I'll talk on the linear system with constant coefficient. Yeah, linear system with constant coefficient. Okay, so again we are still dealing with the discuss the behavior of the trajectories of the phase plane. All right, so in this particular video I'll talk on the how does the behavior of the trajectories for the system of linear equation with a constant coefficient. Okay, now we consider the linear system. Okay, we consider the linear system. Consider the linear system of the form x dot ax plus by and y dot equal to cx plus dy. Okay, where a, b, c and d are constant. Where a, b, c, d are constant. Okay, and we consider the domain D and we consider the domain D to be the whole xy plane. Yeah, to be the whole xy plane. And this domain uniquely defined. Yeah, we consider domain to be the whole xy plane are uniquely defined on t from minus infinity to infinity. All right, now for this system, let's call this system, I give a name. Let's say this equation number 1. Okay, and the characteristic polynomial associated with that system is given as because this system you can write as a x dot y dot is equal to a b c d xy. Okay, you can write as that, where you can write this as in terms of vector notation. So you have a times x. Okay, so where a is those matrix. Now for that you can find the characteristic polynomial. Yeah, the characteristic polynomial with for 1. Yeah, for 1, you know what is the characteristic polynomial. You can find those things. The determinant of a minus lambda I, or you can also write lambda I minus a, just the same. This is, if you do this, you have a minus lambda, right, b, c and d minus lambda. Yeah, that will give you lambda squared. Yeah, if you solve this, you have lambda squared minus a d, so we got a plus d lambda, and plus you got minus bc, that one you got ad there, so ad minus b C. Yeah, for the characteristic polynomial and characteristic equation, you just equate them equal to 0. All right. So for that characteristic equation or augmented equation, the root for that is equation. Yeah, the root is given by or are given by we have lambda 1, lambda 2. This is half a plus d plus minus square root a minus d squared plus 4bc. Yeah, you just find the using those formula. Yeah, using this formula. So the root for that is lambda I is equal to minus b plus minus square root b squared minus 4ac over 2a. So you'll get this thing. Okay, now in general, the general solution of 1, you get something like x minus x equal to c1 a1 e lambda 1t plus c2 a2 e lambda 2t, and y you got c1 b1 e lambda 1t plus c2 b2 e lambda 2t. Now if you look at this, you can see here we have lambda 1, we have lambda 2. Of course, lambda you have a real distinct. We also have repeated roots. We also have a complex root. But if you look at this, we have exponent and exponent. They are almost similar behavior. If lambda 1 is positive and lambda 2 is positive, then the first part and second part give you similar behavior. I mean the similar behavior is that if both are positive, as t goes to infinity, so those t goes to infinity, that c also goes to infinity. Okay, for that reason, we try to simplify the solution without disturbing the original system that we have. Okay, so which means that in this case we do the kind of transformation so that the system that we have here, instead of we have x, instead of we have something like this, x dot equal to ax, now we are going to reduce to the system just like x dot equal to with the roots lambda 1 x and y dot equal to root lambda 2 dot. That gives us a much simpler way, and by doing that, actually we are not touching anything on the behavior of the trajectories for the original system, but we make it much easier. Okay, let's do that. Now to simplify, the description of the behavior of the trajectories, near 0, 0, where 0, 0 is the critical points. So we do the following transformation. We transform, or we use let's say I say zeta is equal to alpha x plus beta y, and eta equal to gamma x plus delta y. This is delta y, where alpha delta minus beta gamma, this is different than 0. So by doing that this transformation, what we have is the point, our critical point, yeah, with that with those transformation, our critical points, which is xy equal to 0, 0, now we transform into that critical point, which is also 0, 0. And conversely, vice versa. So it means that from here you can transform in, we get that, and from that we can transform, we get that. So by doing this transformation, what actually happen now is that this transformation will results, yeah, this transformation, the previous one that I mentioned earlier, transformation will result in a rotation, okay, magnification, or shrinking of trajectories without distort the essential behavior, distort the essential behavior near the critical point 0, 0. Yeah, by doing those transformation, what we actually do is we transform the equation 1 or the system 1 into the new system in the form of that equal to say lambda 1 that, and eta dot equal to lambda 2 dot. Okay, we transform into those things. So what actually happened by doing this, now if you look at the solution, our general solution to the system 1, we have the general solution is given by, I've written somewhere, where is it? No, here. Yeah. Okay, the general solution is given by this. Alright. Now, by doing this, and what's the difference if I just write this as, you know, just change the notation with lambda 1x y dot equal to y. Now, the general solution for this system, we have x is equal to a function of like c1 e lambda 1 t and y equal to c2 e lambda 2 t. So we still have those exponential behavior for x and y. Now we are going to study this that behavior. Okay, now having that in mind, that's the characteristic polynomial with the respective roots of that characteristic polynomial. Okay, then we consider a couple of cases. Basically, we have three main cases. Yeah, we have three main cases. Now we study with the root, which is lambda 1, lambda 2 of the characteristic polynomial, characteristic polynomial of system 1, characteristic polynomial of system 1. All right, we consider, or we have, I would say, we have three main cases. So what are these cases? The first one is that, case 1, you have lambda 1 and lambda 2, lambda 1, lambda 2 are real, distinct, and both are not zero. Both are not zero. Okay. In order to have this kind of roots, in order to have this kind of roots, if you look at the general root that we have, lambda 1, lambda 2 is equal to half a plus d plus minus square root a minus d squared plus 4bc. Okay, now in order to have lambda 1, lambda 2 real and distinct, so what we need, anything in the square root must be positive. So the first condition is that we must have the first condition we must have ad squared plus 4bc, this one must be positive. Okay, now bear in mind that we are going to investigate the behavior of the linear system with constant coefficient. Now, if we do the transformation, zeta equal to cx plus lambda 1 minus ay and eta equal to cx plus lambda 2 minus dy, then our system, then system 1 that we mentioned earlier, system 1 is transformed into we have zeta dot equal to lambda 1 zeta and eta dot equal to lambda 2 eta. Okay, this is what I mentioned earlier, the purpose of doing the transformation, so we can reduce into that system, and then from there just change the notation. Instead of zeta and eta, so we have x and y. Okay, now with that in mind, we consider, now we can consider the system x dot lambda 1x y dot equal to lambda 2 y, where lambda 1, lambda 2 satisfy the condition given here in the case 1, lambda 1 real, distinct, and both are not zero. Okay, now the solution for that system, let's call this as equation or system number 2. Okay, so the system, the solution of, or general solution of system 2, general solution of 2 is given as x equal to c1 e lambda 1 t and y equal to c2 e lambda 2 t. Okay, now for this case, remember that lambda real, this lambda is real and distinct. So you may consider either both are positive, because it's real, positive is real, both are negative, or they have different sign. This one negative, this one positive, or this one negative, or that one is positive. So from there we can split into three different cases or sub cases, I would say. Okay, now remember that I can have a same sign, either positive positive, negative negative, or different sign. Now let's consider those things. Okay, first case, let's put A, first case. If lambda 1, lambda 2 have the same sign, have the same sign. So what happened to have lambda 1, lambda 2 the same sign? We need AD minus BC, this must be positive. Okay, to have lambda 1, lambda 2 same sign, then AD minus BC must be positive. You can try to find out this thing. And then remember that we have a same sign, means we have to split into two cases, either both negative or both positive. Now let's consider for both negative. Now we consider for both lambda 1, lambda 2 negative. Both are negative. Which means if both negative, we must have a condition A plus D is negative. You might ask, where does A, D, B, C come from? This is come from the general or the coefficient of the linear system that I given earlier, which is 1. Okay, if both are negative, and in such a way that lambda 1 less than lambda 2 negative. You can put it either way. You can have lambda 1 less than lambda 2 less than lambda 1, or lambda, I put it that way, lambda 1 less than lambda 2. Okay, so if you look at the general solution that we have, x equal to c1 e lambda 1 t and y equal to c1 e c2 lambda 2 t. Okay, so if t, remember that lambda is a negative number, so if t goes to 0, t goes to infinity, this is the way we analyze the trajectory. The purpose is now to analyze the trajectory, to see the behavior of the trajectory of the system. So t goes to infinity. So what we have, x, what happened to the point xy? If this goes to infinity, remember this is a negative, so we have x goes to 0. S goes to 0, as well as y, because y is also negative, this is also 0. Okay, so, and if you consider the slope of our system of that, so which means if you differentiate this, what we have, x dot is equal to c1 lambda 1 e lambda 1 t, y dot is equal to c2 lambda 2 e lambda 2t. All right, then you can have to find the slope of this, you can have y dot over x dot, and that give you what we have c2 lambda 2 over c1 lambda 1, okay, e lambda 2 minus lambda 1 t. Okay, and remember that lambda 2 is bigger than lambda 1, so what we have, both are negative. This is bigger, so we're going to have a negative number, correct? Okay, so no, sorry, become this become positive because lambda 1 smaller than that's bigger. Okay, so this become positive, so this part become positive. So as t goes to infinity, so what happened to y dot x dot? This also goes to infinity, infinite. Okay, so we have these properties. So one here, we have one here. All right, and then again, if here, what happened at y-axis, what happened x-axis? So if we take c1 0, then we have the rectilinear trajectory. Yeah, we have the rectilinear trajectories. So what happened there is that our trajectories, if I can denote that as c, so we have x is 0. X is 0. So we have x is 0, and y is c2 e lambda 2t. Okay, and similarly, you can consider if c2 is 0, then our c is x equal to c1 e lambda 1t, and y is 0. Okay, now we're going to plot the phase plane, yeah, and see the trajectory. So if this is our axis xy, okay, that's axis xy. So we have on x-axis, as t goes to 0, this is negative, y also goes to 0. So we have something like that on x-axis, and on y-axis, this one this one is y-axis, this one for x-axis, so this one is for y-axis. So we have that. Okay, the arrow to inside 0 0, because 0 0 is our critical point. The reason for that is that when t goes to 0, you can see here, when t goes to infinity, then lambda is negative, and then we got x approaches 0 0. Okay, for others, we have the rectilinear, we have this xy with those properties. All right, xy goes to 0 as x t tend to infinity. So for x and y, so we have x y. Okay, so we have that, we have that. Okay, we have that, we have that. Okay, and the arrow as t goes to infinity, xy goes to 0. So all xy goes to 0. So we have this arrow. Okay, so remember that, bear in mind that this is for the transform system. For the original system, transform system this is for the system 2. Yeah. For the system 1, as we mentioned earlier, the transformation will not distort the trajectories, the behavior of the trajectories near 0, 0, which means we still have that form or that kind of trajectories, but with no rotation or magnification or shrinking, which means I can say, therefore, for system 1, if it happen to be a rotation, we might have something like this is, let's say, rotate on 45 degree counterclockwise, 45 degree clockwise. So let's say it's rotate that way. Why? You can have rotate the other way, no problem, because we don't have a specific direction of rotation, but it's just a rotation. Okay, so we have those straight line, give that straight line, give that, and then you have this arrow there. Let me do this. So we have that, we have that. Okay, and same thing this side, we have that, and we have that. So obviously, if you look at the my first video or second video, that if you take a limit of the solution, it goes to the critical point, then it gives you the asymptotically stable. Yeah, for this case, we have asymptotically stable. So 0, 0, our critical point 0, 0 is asymptotically stable. Totally stable. Okay, so this is for the case of, for the case of, we have which case? We have case 1. Yeah, we have case 1. Recap this. We have case 1. Lambda 1, lambda 2 are distinct, real, distinct. Okay, and then subcase of that, they are distinct but having the same sign. Then we consider both negative. So for both negative, we have asymptotically the 0, 0, the critical point 0, 0 asymptotically stable. The main point that you need to remember is that you need to remember this. Yeah, this is the condition that you need to remember, because in order to have lambda 1, lambda 2 real and distinct, of course you need everything inside the square root must be positive. So that's why we have a positive there. And then to have both negative, you need a plus d must be negative. So you can see it from there, you can see from here. Yeah, if this one is negative, and that one is negative, also negative, and plus positive, because square root of that is this, you got much bigger. So basically you have both a negative sign. Both you have negative sign if that one is bigger than that one. Yeah, that's positive. This is sorry, if this one is smaller than that one, so you got a negative sign. So you need that condition. Okay, with that condition, we have shown that our solution is asymptotically stable. Now we are going to go for the what happens if both roots are positive. Yeah, I think I have to stop here because it's already 35 minutes. If I go beyond than this, my handphone might hang. I got problems, though I have to stop here. Then I could continue in the next video. Okay, so for now, bye bye.